In our previous video, we talked about equilibrium and equilibrium expressions. So just to give a quick recap on everything we covered, we said that if we had a K value that was greater than 1, well then our concentration of products will be greater than our concentration of reactants at equilibrium. Conversely to that, if we had a K value that was less than 1, we were saying that our concentration of reactants was greater than our concentration of products at equilibrium. And if our K value was equal to 1, well, our products and reactants had the same value. In other words, what we had in our numerator was divided by that in the denominator. So I'll just write same values. So in this video, what we're going to do is we're going to tie it all in and show how there's a relationship between K values and free energy. Or more specifically, we are going to demonstrate that there is a direct relationship between delta G standard and equilibrium, or equilibrium expressions. So let's just demonstrate that, and we can start off by showing, I suppose what we can do is we can just dive right into it, and we can say that if we have a K value that is greater than 1, well, we are going to have a delta G standard value that is going to be negative. And if we have a K value that is less than 1, then we will have a delta G standard value that is positive. And if we have a K value that is equal to 1, we will have a delta G standard value that is equal to 0. So let's just prove this and demonstrate why this information is correct. So let's start off by using an equation. So you're going to use delta G equals delta G standard plus RT natural logarithm of KEQ. And so let's just describe what all of these are. So first we have delta G, and that's going to represent free energy, or a change in free energy. So I'll just write change. And energy can be denoted by the capital letter G. Delta G standard is going to be a change in energy, but they are going to be under standard conditions, and that's what this little degree symbol up here is denoting. So I'm going to write STP, and that's under standard temperature and pressure. Remember that the standard temperature is going to be at 25 degrees Celsius or 298 degrees Kelvin, while pressure is going to be at 1 atmospheric pressure. And since we are working with this equation and we are speaking in terms of equilibrium, we are also going to say that our Q value, or our reaction quotient, is going to be equal to 1. And if you forget what the reaction quotient is, you just go back and check in any textbook and look under equilibrium, and you can just do a quick reference into that. But basically now we're into R, and that's going to be the ideal gas constant, and we are going to use 8.314 joules per mole times Kelvin. Temperature will always be represented in Kelvin, and you can easily convert from Celsius to Kelvin simply by adding 273 or 273.15. Just check with your instructor or textbook to see which value you will be using to input into your calculator to demonstrate your calculations and show your answer. But either way, it'll be 273 or 273.15. Now, we've already talked about equilibrium, and so I'm just going to show equilibrium right here. So now there's another part to this equation that I want to mention, and I think if I mention this will avoid confusion further down the road. So first off, I want to talk about the left side of this equation, and I want to demonstrate how it's different from the right side of this equation. So delta G and delta G standard are representations, and they explain things thermodynamically. So I'm just going to write thermodynamics. While KEQ is going to represent and explain things kinetically. Because remember, with KEQ, what we are saying is that we are establishing a concentration at a point at which the rate of the forward reaction is equal to the rate of the reverse reaction. So since we are working with rates, we are working with kinetics. Now just to differentiate between thermodynamics and kinetics, I want to say that kinetics represents speed of a chemical reaction, while thermodynamics represent spontaneity of a chemical reaction. So now remember, with kinetics, when we are speaking in terms of equilibrium, because that's the next point I want to make, I want to say that when we call something out as being in equilibrium, we are going to want to reference whether or not we are speaking in terms of thermodynamics or if we are speaking in terms of kinetics. So I want to make that point moving forward. Now remember, to be at equilibrium with kinetics, I'll just change colors here to show emphasis, but I'm going to say at EQ, and that's for equilibrium. So at EQ, the rate of the forward reaction is going to be equal to the rate of the reverse reaction. Well, with thermodynamics, at EQ, delta G, or delta G standard, is going to equal 0. And that just basically means that you have a balance of free energy, and that there is no difference from one side to the other. And that can also be explained and described by simply saying that there is no spontaneity. And no spontaneity does not mean non-spontaneous, because remember, non-spontaneous means that we are going to require an external input of energy in order for a reaction to take place. So we are not saying that, we are just saying that there is no spontaneity, meaning that there is not a non-spontaneous reaction and there is not a spontaneous reaction. Therefore, there is just no spontaneity, and that's how we are able to say that delta G or delta G standard equals 0. So I want to make that point. Now briefly, I want to describe why and how we have a delta G value that equals 0 at equilibrium. Because I'm sure in your textbook you've already seen that at equilibrium, delta G equals 0. So let's just explain why that's so. And I think the best way to describe that will be by using a Gibbs free energy diagram. And we can show a couple of them, or a few. We'll show another one right here. So let's show some reactions. So we'll start off with the spontaneous reaction, where we start at a lower or a high energy and we end at a lower energy level. And we'll make these our products. Over here are reactants. And conversely to that, we will show a spontaneous reaction doing the complete opposite of what we've just drawn. And once again, these are products, reactants. Now the next thing I want to mention is when we are moving from this spontaneous reaction, we will see that if we trace these energy levels or differences in energy levels, we should show a negative delta G value. And conversely to that, when we are showing the non-spontaneous reaction, if we trace our energy levels, we should demonstrate that we have a positive delta G value. And so now the next question is, well, how do we have a delta G value that equals 0? Well, I suppose if I were to just arbitrarily assign values to these negative delta G's and positive delta G's, I could say that this negative delta G equals 50 kilojoules per mole, or in other words, negative 50 kilojoules per mole. While over here, this positive delta G is going to equal positive 50 kilojoules per mole. Because remember, at equilibrium, we are moving in the forward and reverse reaction. So I'm kind of saying that, from here, we move from here to here, moving in this direction, and I suppose I can just show it all the way through. Well, to go backwards to this, that would be this side, or this middle graph right here. And I'll just show that we are moving in the opposite direction, or actually, this right here would be an indicator of us moving backwards from this reaction. But either way, you can see that we have negative 50 kilojoules per mole moving in the forward direction, and we have positive 50 kilojoules per mole moving in the reverse direction if we are referring to this same graph. But I've shown this additional graph here to demonstrate it as if we have two different reactions. But really, these are both the same reaction. And I'm just going to write that right here just to avoid confusion. So overall, we are going to have a delta G value that equals 0. Looks something like this, where basically there is no change in free energy. So I'll just write delta G equals 0. And that's exactly what I've said over here. So that is how we are able to show that delta G equals 0 at equilibrium. Now let's just demonstrate one additional example to this for people who are more mathematically inclined. So let's see here. I suppose I can show something like this, because remember, at the beginning of the video I've demonstrated this equation. Delta G equals delta G standard SRT, natural logarithm of KEQ. Well, if delta G equals 0, as we've indicated here, we are going to have a delta G standard plus RT, natural logarithm of KEQ. Now the next thing I want to say is that this delta G standard value can be the negative 50 kilojoules per mole, and then this RT ln KEQ could represent our positive 50 kilojoules per mole. So when you add these two together, you end up with the 0 value, as indicated here. So that's another depiction of how we are able to gain this delta G value at 0. Now sometimes these don't act accordingly, because remember, when we say that delta G equals 0, and that's typically how it's going to be presented to you with a test or a homework assignment perhaps, you don't necessarily know what these values are. And when I'm saying these values, I'm talking about this graph and this graph. I mean, they may not equal out to 0. And if they don't, well now you're not going to have, you are going to have spontaneity. And remember, if we want it to be at equilibrium thermodynamically, well we do not want spontaneity. So basically we need to just double check this work, and that's why this delta G value equals 0, and that's kind of our baseline, if you want to think of it that way. And really what we're trying to determine is we're trying to determine how far off we are from that value, and by showing that we can demonstrate spontaneity from that. So anyway, let's just keep moving forward and show some additional reactions and demonstrations of this. So let's just see here, show our equation again. So remember, at equilibrium, our delta G is going to equal 0. Now, if we just manipulate this algebraically, and all I really did was I took this positive RTL and KEQ and moved it to the other side of the equation, so there was no magic there. But basically, this is the equation that you're probably used to seeing, and this is the equation that you use often. Now with this equation, we can immediately see that there is a direct relationship between delta G standard and equilibrium. And that's what I said at the beginning of this video. And keep in mind, I mean, just looking at it from this point of view now, we can see that if we manipulate KEQ, well, that's going to have an effect on our delta G standard. And conversely to that, if we manipulate our delta G standard, we will have an effect on our KEQ value. So let's just show some additional examples to this. Now, I said that in the beginning of the video, I was going to tie all of this in. So let's just start by saying, in this case, if I have a K value that is greater than 1, and I plug it into this KEQ, well, my result is going to be delta G standard equals negative. And over here, if I have a K value that is less than 1, I plug it into KEQ. Well, now I'm going to have a delta G standard that is going to be positive. Over here, if I have a K value that is equal to 1, and I plug it into my KEQ, now I will have a delta G standard value that is equal to 0. And I can explain this briefly by simply saying that, I mean, if I have a KEQ value equal to 1, well, remember, the natural logarithm of 1 is going to be 0. So it really doesn't matter what my R and T values are because, I mean, anything multiplied by 0 is going to be 0. So that's how we are able to demonstrate that. Now, let's just show how this looks graphically. And we can show that if we trace these energy lines right here, we can see that our delta G value, and that's delta G standard, is going to be negative. And by the way, all of these G values are standard. So let me just write that in here. Now over here we can see that our delta G value, or our delta G standard value, is going to be positive. And then over here, there is going to be no change in free energy. So therefore, our delta G standard value is going to be 0. So as you can see, I mean, all of this ties in. And basically what we are saying when we are looking at these two reactions, we are seeing that over here, we have a spontaneous reaction. Over here, we have non-spontaneous. And then over here we have no spontaneity. So you can see that with these two reactions, with the spontaneous and the non-spontaneous, well, these somewhere along the lines deviated from that 0 value that was mentioned up here. So remember, I was saying that if you have a negative 50 kilojoules per mole and you have a positive 50 kilojoules per mole, well, that should equal out to 0. But it didn't. Somewhere along the lines, we deviated from one of these values, and as a result of that, we ended up with either a negative delta G standard, or we ended up with a positive delta G standard. So, in addition to that, I want to say one more thing. Now the next thing I want to mention here is that if we have a value with a spontaneous reaction and a non-spontaneous reaction, we are still going to have equilibrium. We are just not going to have thermodynamic equilibrium. So what do I mean by that exactly? Well, remember, I also mentioned that we could have kinetic equilibrium and thermodynamic equilibrium. So in these two instances where we have a spontaneous reaction and a non-spontaneous reaction, well, we're definitely not going to have a thermodynamic equilibrium because our delta G values do not equal 0. However, we do have a kinetic equilibrium because, I mean, that's what we're using for our values. We're using these KEQs, and that's an indication as to us having a kinetic equilibrium. So I'm just going to write kinetic EQ. Over here, it's the same thing. We have a kinetic EQ. And then over here, we have a kinetic EQ. But we also have a thermodynamic EQ as well. Because our delta G standard value equals 0. And remember, in order to have a thermodynamic equilibrium, we need a value of 0 for our delta G, or delta G standard. And so I want to make this point because I think a lot of textbooks and sometimes instructors will tell you, well, you only have equilibrium when your delta G equals 0. Well, that's true thermodynamically, but I mean, you can still have equilibrium kinetically as well. And so anyway, there's just one last point I think I should bring up, and I'm running out of time here, but basically one of the other questions I would typically have is, well, from that, how could I have a kinetic equilibrium if, for example, my reaction rates are different? And it looks like they're different anyway, because this activation energy barrier is a lot smaller to climb than this activation energy barrier. So my thought would always be, well, how could we have a kinetic equilibrium if these reaction energy barriers, or these activation energy barriers are different in heights or in energy? Well, the short answer to that is, I suppose if you were to ask somebody, how do you speed up a chemical reaction? Well, you'll typically get three answers to that, and the first answer is, well, you can just simply add heat. So I'm just going to write increase heat. Another answer may be, well, you just increase the concentration. And a third answer may be, well, you increase the size of a molecule. And when you increase the size of a molecule, by the way, really all you're doing is just increasing the surface area, if you will, to allow for more probability that molecule can react with another molecule during collision. So anyway, I want to make that point. But the point I want to make too is that what we are paying special attention to in this case is the increase in concentration. Because remember, we have a K value that is greater than 1 in this instance. And if we have a K value that is greater than 1, what we are suggesting is that we have a higher degree of concentration in our products than we do in our reactants. And if we have a higher degree of concentration in our products, that's going to help climb this larger activation energy barrier. Now, on the other side, we have less concentration, but that's okay because we have a smaller activation energy barrier to climb. Now what's going to happen is as a result of this, the rates will actually be the same. So in other words, the rate of the forward reaction will equal the rate of the reverse reaction, and therefore we have kinetic equilibrium. However, we do not have thermodynamic equilibrium unless delta G equals 0. So I hope that video was helpful, and that's basically the connection between delta G standard and equilibrium constants or equilibrium expressions.